Welcome back, physical science kids. Mr. Tima here. This is part two of our electricity notes. We left off, if you want to just flashback real quick, we left off, you finished with the signal circuit lab. All right. So basically, from that, again, we're talking about electrons. So there are parts of circuits and electricity that we need to make sure we have as we talk about things. There are materials. Are there materials that electrons can easily move through? Well, the answer is yes, and they're called conductors. And remember, conductors is kind of like conduction, okay? Materials that allow electrons to move through it easily. Okay, the electrons are loosely held. You can see how the electrons here, if we bring a negative rod up here, it's going to push, because remember, like charges repel. It easily moves them through here. It's going to bring out a positive one. You're going to see that positive one come out, and you're going to see the electrons kind of fly up to it. That's a conductor. The electrons are loosely held, and it allows to move through it easily. Examples of this would be like metals, copper, silver. Gold's not as great because it's a little bit soft, but this is what we're talking about. So think about that. Most wires are made of metal, things like that. You know, if there's a thunderstorm outside, you're not supposed to have a metal pole in your hand, so forth and so on. You guys know that. All right. Are there things that they don't move through easily? Well, yeah, they're called insulators. Okay. All right. Insulators don't allow them to move very easily. So if you notice, they do move a little bit. They move a little bit. You can see that they're moving a little bit, but they're not like before, right? They're not like flying down here to the bottom. Okay. It allows the electrons to be tightly held. It doesn't want them to move as much. Can you guys think of something? So if wires are something that allows it to move easily, a conductor, what would be an insulator? Think of the word insulator, like insulation. What insulates electricity? Well, I hope you came up with like plastic, wood, rubber, glass, basically any non-metal. And if you think about it, if you've ever seen a wire, it usually has like a plastic coating or tube around it, something like that. That's why they say if you have shoes on, you can't get shocked because you have rubber soles, all those kind of things. Okay. And you think about any cord that you plug in, and if you've ever had an iPhone cord that gets frayed, you've known it'll maybe make a little spark or something. But all your outlet covers are mostly plastic, all that kind of stuff. So here's the deal. If you're in class, we'll be able to do this. If we're not in class, it's going to be hard to do. But the idea is work. Work equals energy. If we do work, we're going to use energy. And a lot of times that energy can be turned into electricity. The idea of the hand crank demo is this. There are LED lights and there are regular old phosphorescent lights, which means like the old kind of metal, as we would say, an Edison tube ball versus an LED light. Okay, well, you know that a lot of these produce a lot of heat, and that's where a lot of the energy goes. And you can actually feel with the hand crank how much harder it is to light a regular light bulb versus an LED. LED barely uses any energy, and that's why a lot of our lights now use LED, because it takes a lot less work to produce the energy to make that electricity. Okay. All right, so what is a source? This is what's important. You need to learn these terms. A source is the beginning or origin of electrons in the system. Now think about water for a second. Now a source is actually this right here, is a thing we use in lab and physics and chemistry and stuff. In your wall, we tend to think of the source as an outlet. Okay, but if we're talking about water, a source is like the spigot on the top side of your house. This is where it all comes from. We're either going to turn it on here, we're going to turn it on here, or you're going to plug it in. Okay. Electrons flow from positive to negative. That's important to know. Okay. This is the actual symbol of a source. Okay. And what this is showing you is that as it moves from positive to negative, because electrons come out of the negative end, and that electricity has to flow. Electricity flows from positive to negative. So it kind of goes around here. Okay. As it goes around in the circuit and it comes to this end, well, look, it has to like make this jump. Okay, and that jump requires some energy use. So like a battery for the circuit to keep going has to jump. That jump uses up the chemical energy in the battery. That's why batteries have to be replaced or recharged. Your phone is doing this. Every time you hit a button on your phone, inside it has to make a little itty bitty jump and uses a little bit of electricity. And since it does that, that's why we have to recharge our phones and things like that. Otherwise, in essence, it should just keep going on forever and ever and ever. But we know that that obviously is not the case. Voltage. Voltage is the electrical potential energy per unit charge. Okay, that's a lot. So what the frick does that mean? Well, what does it mean? Voltage is the push or the separation of charges. Okay, so it's the push. So think of like a water tower, for example. If I make this water tower really high, okay, is there going to be more push or less push? It's going to have more push the higher this is because there's going to be more gravity. There's going to be more time for gravity to act on it. If this was a bigger tank, it's going to have more push, okay? Because voltage is all about the push, okay? So think about about the hose again. How do we increase the push that comes out of the hose? How do we increase the amount of water coming out of the hose? Do you turn the spigot on a little bit, or do we turn it and open it all the way? Well, we open it all the way. That's what that is. So voltage is the push. Okay, everything that I just talked about to you is just written right there. Okay, so you can look at that if you want. All right, current. Current is the flow. Okay, current is all about the flow of electrons. Okay, so for example, if we have the same push, okay, if we have the same push, we have the same size tank, there's the same amount of push coming out of the house. Okay, but I have a really skinny hose and I have a really kind of fat, open, wide hose. A lot more water is going to come out of that bigger opening than the smaller opening. You can also think of it like this: if you're in a little backyard water war and you were to have the hose in your hand and you can't turn on the spigot anymore, like you can't turn it up anymore to get more water out, how do you launch water farther? Well, you put your finger over the end to resist the flow, which creates that like spring or that like kind of like jet of water. Okay, it depends on the number of electrons passing per given point of time. It's measured in something called amps. The symbol is A, okay, which is equal to the number of charges per second, which you don't really need to hold on that. So remember, voltage is push, current is flow. All right, and then current again can all depend on having more resistance or less resistance, okay? So, what is resistance? Resistance is an opposition to the flow of electrons. Electron energy is converted into either light or thermal. So, a light bulb, a light bulb, in essence, that wire is what we call a resistor. It's using up the energy of the electrons by either producing light or heat. Okay, it's measured in something called ohms. Okay, but the idea is high resistance equals no flow equals no current. Okay, so if you have absolutely 100% resistance, you'll have no flow of electrons. Okay, I like to think of it as again a water versus like a battery picture. So here's our reservoir. That would be like where it's sitting in the ground outside your house. It comes up to the pump. The pump is like the battery. Okay, and that pump pushes the water. Well, that pushing of water is the voltage. That's the voltage, the push. Okay, as it flows around, that's the current. Okay, that's the current, the flow. Okay, and then as the flow reaches this little narrow neck in the river, you know what's going to happen here. What's going to happen here? This water all gets shoved in here. It gets flies through there, but it has to slow down over here. And it slows down here because it only has so much room to get through. That would be the resistance. And then again, it would flow back around to the pump. And that, again, that's the currents. The current would be flowing this way, just like it's flowing this way. But you see how that kind of, this is a resistor, this is a resistor. The pump, the voltage, the push, the batteries right here. All right. So resistance. Resistance depends on the conductor, what it's made of, the wire thickness, less resistance in thicker wires. Now that might not make sense unless you actually look at something here, and we're going to look at it here in a second. Okay, wire length, less resistance in shorter wires. Temperature, there's less resistance at low temperatures. Okay, so let's look at the first one. It says wire thickness, less resistance in thicker wires. You might think, wait a minute, Mr. Tima, if something's thicker, shouldn't it resist more? Remember, thickness is not density. Okay, so for here, this is kind of what we call resistivity. But let's think of this A, which is the area, the cross sectional area. Every dot would be an electron trying to come through there. watch what happens as we increase the area and make it bigger. Look what happens to R. R gets really small, which is the resistance, okay? So let me come back down here again. So it said the thicker the wire, the less resistance, which actually makes sense because the thicker the wire is, the more electrons can fly through this. This is like having a bigger pipe, okay? So again, the thicker the area or the bigger the area, the thicker the wire, the less resistance. And the counter is true. The smaller the area, look how big that resistance gets. Okay, that would be like you trying to put out a hooking a straw up to a fire hose. It would be really hard to get that water through there. Okay. All right. The other one said wire length, less resistance and shorter wires. Okay, let's look here. So this is the length of the wire. So the greater the length, look what happens. The resistance goes up because even though there's more room in there for particles to flow, still every time those particles are in that wire, it's using up a little bit of energy. So if the tunnel's longer, it's going to spend more time losing a little bit of energy. Okay. So what it said is the shorter the length, the less resistance. I mean, look at that. If we barely have anything, boom. Think about this, a water coming out of a fire hydrant. If there was a hose this big and the hose was the resistance, it would just shoot right out. It's like the hose wasn't even there. If it's a super long hose, the resistance would be bigger. All right. And last but not least, it said temperature. Okay. Less resistance at low temperature. Okay. You have to think about this. Now, I can't show it to you on the other one, but what you have to imagine is if the wire are these red things at lower temperatures, okay, these little red things, these protons aren't moving very much. So there's like a little pass for the electrons to get around. If it was at higher temperatures, these red balls would or protons would be bouncing around a little bit, causing like little moving traffic jams for our electrons. So the lower the temperature, the less resistance. Again, here's just another picture of it, just so you know, kind of like a water demo versus an actual battery. Again, here's the flow, that's our current. The resistance in this one are seashells, if you will. Okay, this would be our resistance, and then you have the flow, and the pump would be our voltage. All right, we have another little simulation lab here. I know those notes were a little bit longer, but hopefully you enjoyed them. This one has a lot of cool stuff, and you're going to see how that temperature really affects in this one. All right, ask questions. I know that.